Okay, so welcome to proofs, guys. So we are going to get into what is kind of the key cornerstone of upper mathematics. Okay. Um, so the idea when you're proving things, writing out a proof, is going to be a story. It's a closing argument. It's a series of logical steps, but written stylistically. So let's just jump in and go. The more and more examples we get, the more comfortable you'll be with it. Okay. So for starters, we are going to start focusing on things of the form P implies Q. If P, then Q. So if you remember our truth tables, the only time P implies Q is false is if P is true and Q is false. Okay, if P is false, it doesn't matter what Q is, the statement's true. If P is true and Q is true, the statement's true. So this is our only problem. This is the only situation we need to avoid. So this means we need to show P true. If P is true, it's going to guarantee, so P true guarantees Q is true. That's what we need to show. Okay, if P is true, it's going to guarantee Q is true. If I can show that, I have ruled out my one bad situation. Okay, once I rule out my one bad situation, then I can declare the statement true. All right, so the way we're going to do that, we are always going to start by assuming P is true. Okay, assume P is true. That did not highlight well, did it? Assume P is true. Okay. Then we can fall back on definitions and previously proven facts, whatever we've got to show Q must be true. What do I mean by definition? A definition, well, that's just our agreed upon meaning of a word. And a theorem is going to be a proven fact. For the purposes of this course, we will have some theorems that we don't actually prove. Normally in math, you'd call that an axiom. An axiom would just be a fact you just assume is true. Okay. So, but in most courses, pretty much every fact you do, you're going to prove from scratch. So if we're going to use definitions, we'd better get some definitions down that we can agree upon. So let's start with what will end up being probably your favorite of all the definitions. So an integer n is odd. You know what odd means based on like elementary school odd, but for math, we need something more rigorous, more definite. Okay, so here's how we're going to define it. Is odd if and only if, let me switch colors. There exists a k in the integers such that n is 2k plus 1. So that's how we're going to define odd. It is twice an integer plus 1. Okay. Even is going to be similar then. It's even if and only if there exists k in the integers such that n is 2k. So this means whenever a statement says an integer is odd, I can jump to writing it in that form. You know, when it says an integer is even, I can jump to writing it in that form. Okay. And that gives me something to work with. All right. Some other related language. two integers have the same parity, and only if both are even or both are odd. And it's just easier to say same parity than to say both are even or both are odd. Okay, so opposite parity is going to mean you have one of each. So one is even and one is odd. Doesn't matter which one's which. Any questions on those definitions before we start using them? Okay, so let's do our first proof. We are going to prove that the sum of two even integers is even. Okay, in order to do that, we're going to have to identify our hypothesis and our conclusion. Then we are going to, oh, is parity like a pair? Yes. So you could say parity relates to pair is why we have to have two. Yep. Similar root word probably. Okay. So in order to prove something, we need to identify hypothesis and conclusion. Then we're going to do our scratch work where we look up whatever definitions of theorems we need. Then we're going to figure out what our logic is. Then we'll write up our proof. This step, that's all you turn in. Okay. That fourth step is all you turn in. Okay. So here we go. I need to get this sentence to an if-then statement. So I look at it, prove that the sum of two even integers is even. So what we're saying is if A and B and the integers are even, then A plus B is even. That's what the statement's saying. If I have two even integers, when I add them, then it's even. Okay, so that means I'm going to be assuming A and B are even, because that's my hypothesis. And then I want to show A plus B is even. So let's see how we go about doing that. Here's where our scratch work comes in. All right, so if I'm going to assume A and B are even, so this is my scratch work, I look back at my definition. What's it mean to be even? Well, that means there exists a k in the integers where a is 2k, and there exists an L in the integers where b is 2L. Notice I had to use two different variables here because k and L, they could be the same number, but they're probably different. So I needed to represent them with different variables. All right, I could have used X and Y if I wanted, or Z and W, whatever. I just like K and L, so that's what we'll use. Okay, so when I assume A is even and B is even, I use the definition so I can rewrite them into a new form. Then I look at what I want to show. My goal is to get that A plus B is even. Well, what's that mean? That means I need to get A plus B to be 2 times something. That would make it even. 2 times an integer is even. That's our definition. All right, so I'd better look at A plus B to get to my goal. Well, A is 2K, B is 2L. Say, oh wait, I can factor that 2 out because that's the distributive property. So if I pull that 2 out, I now have the form I want because K plus L is an integer. K is an integer, L is an integer. When I add them, it's still an integer. So I do have the form 2 times an integer, which is what it means to be even. Okay. Any questions on the scratch work before we write up the proof you would turn in to go with this? All right, so let's write up what you would turn in. So after you've got your scratch work, you go to a clean sheet of paper and you write up your answer. So it'd be proof. You always start a proof with what you're assuming, and you always use complete sentences. So I am starting by saying assume A and B in the integers are both even. And there are lots of different ways to say that statement, but somehow you need to start by saying you have 2 integers and they are both even. Okay. Now we just go through our logic, but using complete sentences. Then, by definition, that way I'm referencing what I'm using. I'm using the definition. Okay. There exist K and L in the integers such that A equals 2K and B equals 2L. All right, so I just used the definition. So I like to use the word note that. So we'll say note that. Now I'm going to put my string of equations. A plus B equals 2. Oops, I jumped ahead. 2K plus 2L equals 2K plus L. Period. All right. And then I think, what was my logic here? Oh, if I have 2 times an integer, that's what it means to be even. So I need to argue that K plus L is even. So we can say since K is an integer and L is an integer, K plus L is an integer. Thus, A plus B fits the definition of even, or you could just say A plus B is even. All right, and that was our ultimate goal. That's what we needed. We needed to show A plus B is even. We showed A plus B is even. So we have finished our proof. At the end of your proof, typically we'll put a box. Some people leave an empty box. Some will put lines in it. Some will shade it completely. The point is the box is signifying I have ended my proof. I have ended my logic. All right, a proof, a well-written proof, you should be able to just read it like a story, okay, or like a closing argument to a jury or something. It should just flow and read, okay. Between symbols and words, it still should just flow. So, what questions do people have on that one? Okay, cool. Well, let's look at another one then. All right. Prove that if x and y are positive real numbers, then that crazy inequality holds. So this one already split off my hypothesis and conclusion. So if x and y are positive real numbers, that's what I'm going to assume. Then this crazy inequality, that's what I need to show. So scratch work time. All right. So I'm assuming x and y are positive real numbers. Well, there's not much to work with there, right? So we look at that and go, I don't have definitions to fall on. I don't have a special form to write those in. So how do I get this inequality? So that's when we go down to our goal and try to work backwards. So our goal is 2 square root of xy is less than or equal to x plus y. Well, let's square both sides and see what happens. So that would give me a 4xy less than or equal x plus y squared. All right, well, let's write out what x plus y squared is. That's x squared plus 2xy plus y squared. Okay, say, oh, I'm going to subtract 4xy from both sides. If I'm adding or subtracting, it doesn't change my inequality, so that's okay. So I'll have 0 less than or equal to x squared minus 2xy plus y squared. And that actually factors because that's a perfect square. That's x minus y squared. So what I've been doing to this point, I've just been playing with it, rewriting it until I get to a statement that I look at and say, hey, that is always true. Okay. So if I take any number, I don't care if x is bigger than y or if x is smaller than y, when I square it, it is going to be less than or equal to 0. Okay, so anything squared, any real number squared is greater than or equal to 0. There we go. So that statement's always true. Something that is always true, you can state at any point you want in a proof. So here's how a work backwards proof goes. I am going to start here and then work down to my goal. I just have to be very careful at every step, okay, making sure that my steps reverse okay. All right. So let's write out our proof. Again, all you'd turn in would be the proof. So we start with our assumption. I'm going to assume x and y are positive reals. Okay. So here we go. Let's go to our start. I'm going to say since r squared is greater than or equal to 0 for any real number, we know 0 is less than or equal to x minus y squared. All right. Thus, here we go. I'm going to do my string of equations. 0 less than or equal to x minus y squared. 0 less than or equal to x squared minus 2xy plus y squared. And now I look at my work and say, oh, I need to add 4xy to both sides. All right, and that is x plus y squared. So again, I'm just reversing my work. Okay, now here's where I have to be careful. I'm going to take the square root of both sides. So 4 square rooted is 2. Square root of xy is well defined because x and y are positive. So when I multiply them, it's positive. I'm not taking the square root of a negative. Then when I take the square root of a square, so little side note, you may or may not remember from calculus, the square root of a square is the absolute value of that number, right? Because technically you can take a negative and square it to get positive, then square root it. So technically here, I'm getting absolute value of x plus y. You may think, well, crap, all hope is lost, right? No, it's okay. All right, because x and y are positive. So since x and y are positive, that is the same as x plus y. So we need to write that in a sentence. That last step, we did a lot of justification. So we want to write that in a sentence. Note that xy is greater than 0. So square root of xy is well defined. That means it's allowed, right? I'm not taking the square root of a negative. And x plus y is greater than 0. So absolute value of x plus y equals x plus y. All right, so we justified our last step. Oops. Now we're done. We've shown what we need to know. So thus, 2 square root of xy is less than or equal to x plus y. And box. All right. Any questions on that one? All right, let's keep on going. Okay, so now let's do a new definition that we can work with. So we're going to look at this word divides. So if I have m and n in the integers, we're going to say m divides n, and we are going to notate it with that straight line. And that's going to mean n equals m times k for some integer k. One way to think about this is m divides into n. Okay, that's what we're saying. M is a factor of n. All right, n is a multiple of m. All those words. Mathematicians are just lazy and take the shortest, which is divides. So let's look at some examples, make sure we understand this. So for example, we would say 5 divides 15, right? Because we need 15 to equal 5 times something. That's an integer. Well, what is that something that's an integer? It's 3. Okay, so I was able to find some integer k that worked. In this specific instance, it was 3. 5 does not divide 24 because there is no integer times 5 that will equal 24. Okay. I mean, you could do 24/5, but that's not an integer, right? So I don't fit the definition of divides. Now, what's interesting here is 0. So let's do a few cases with 0. So let's check 0 divides 3. 3 divides 0. We're going to see if any of these are true. And 0 divides 0. All right. 0 divides 3. That would mean that 3 equals 0 times something. Well, definitely not. So that one's a no. Okay. What about 3 divides 0? That would say 0 equals 3 times something. That one actually works. Okay, because 3 times 0 is 0. So 3 does divide 0, but 0 does not divide 3. So 3 divides into 0, 0 times. 0 does not divide into 3. Okay, so this one is interesting. If you remember calculus, trying to do 0 over 0, that's an indeterminate form and funny things happen. Let's see what happens with this definition of divides. 0 equals 0 times something. This is actually true. I can put any integer I want in there. So let's put 17, right? There does exist an integer. It doesn't say in my definition that there's one specific k that works. It just says some k. So if you can find one that works, then the answer is yes, it divides. If there's more than one that works, which is 0 divides into 0 is the only case that happens, technically that works. So that's a yes. Any questions on that notation and that concept before we do a proof with it? Okay, so let's look at a proof. We want to prove that whenever A divides B, so that's my if, so that's my assume, that we must have A divides BC for any C. That is my show. All right, scratch work. So I'm going to assume A divides into B. A is a factor of B. Then I think back to my definition. What's that mean? Well, that's going to mean there exists a K in the integers with B equal to AK. That's what the definition meant. My goal is A divides BC for every C in the integers. So that means I want BC to equal A times some sort of integer. If I could get BC to equal A times some integer, then A divides BC, because that's what my definition says. Well, look at this, B equals AK, and I want BC. So I have B, I want BC. So why don't I multiply both sides by C? So we have BC equals AKC. And that's what I want, because K is an integer, C is an integer. Doesn't matter if C is 0 or anything, when I multiply, K times C will still be an integer. Positive, negative, 0, it's still an integer. It's not going to magically get a fractional part. So now we're ready for our proof. And again, all you turn in is the proof. You don't turn in the scratch work. So actually, let me phrase this differently. We're going to start the same way the problem did. Let A and B be integers such that A divides B. So that's my assumption. That's what I'm starting with. All right. then by definition, oops, sorry. By definition, there exists k in the integers with b equal to ak. Now, a few comments. It's very important here that I stated what type of number k is. Whenever you're bringing in a new number, you have to declare what it is. This k is very, very specific to whatever a and b are. As a and b change, it'll change, but it is an integer, okay? All right, my next step was to multiply by c, so I'd better declare what c is. So we are going to say, let c be any integer. Now we're being specific about that. We're making c arbitrary because that's what the problem wants. The problem specifically says this has to be true for any integer c. So that's why I'm declaring it like that. So let c be any integer. Then, well, what did we do next? We multiplied our equation by c. bc equals akc. All right. Now in my scratch work, I looked at it and I said, oh, I need k times c to be an integer. So that's the next thing I need to justify. And then I have what I need. So since k, c are in the integers, kc is an integer. In fact, if I wanted, I could replace k times c with the letter L and say L is an integer. Okay, some proofs will do that. I like to normally just leave it k times c. So since k, c are integers, k times c is an integer. So bc equals a times kc implies a divides bc. And technically we could end it here. I'm just going to write a little more. We're going to say since c was arbitrary. What I mean by that is c didn't depend on anything else. It could have been any integer I wanted. Okay. So since c was arbitrary, a divides bc for every integer c. And now I'm going to box it off. Done. All right. Any questions on that one? Okay. And remember, with these proofs, when you go back and read over it, you should be able to just read it like you would a story. Okay. It should flow and use complete sentences. All right. So in general, for this class, you can just assume the sum, difference, and product of two integers will still be an integer. All right. Now, obviously, the quotient won't, 2 divided by 3, that's not going to work. But the sum, difference, or product, that will be, you can just assume that and use that fact like we have been. Okay. But let's not assume that for rational numbers. Let's actually prove that the sum of two rational numbers is a rational number. Okay. All right. Move this over. So I need to identify my if and then because this one is in a funny form. So my if, we're going to have two rational numbers. So x and y are rational numbers. Then x plus y is a rational number. So I need to assume x and y are rational. And I need to show x plus y is rational. So that's my goal. All right. Scratch work. So I'm starting with x and y being rational. Well, that I can actually get a handle on because I know what it means to be rational. It means x is a over b and y is c over d. And this is my scratch work, so I can just say all integers and b and d are not 0. We'll write that nicer when we write up our proof. But that's just a reference to myself. A, B, C, D are all integers, and B and D can't be 0. All right. So my goal is to get x plus y to have the form something over something, integer over integer. Okay, integer over not 0 integer to be more specific. So I'd better look at x plus y. Well, x is a over b, y is c over d. Do common denominator, we'll get AD over BD plus BC over BD, AD plus BC over BD. All right, so that was just algebra in there, but I did get to the form I want. I do have an integer, and I do have an integer. The question is, am I dividing by 0? Well, no, B isn't 0, D isn't 0, so their product can't be 0 either. Okay, so that's good. That's the form I want. So now I'm ready to do my proof. And again, all you turn in is the proof. All right. So let's suppose x and y are rational numbers. Then there exist A, B, C, D in the integers with, let me go ahead and move this over, with B not equal to 0 and D not equal to 0, such that x equals a over b and y equals c over d. Okay. Now, here we go. Now we're going to write out our algebra. X plus y equals a over b plus c over d. We don't have to put every single step in our algebra. You can assume your audience, okay, your jury, let's say, can do basic algebra. So you can jump to this last step, AD plus BC over BD. Okay. All right. So now we just need to justify, yes, that is the form of a rational number. So since A, B, C, D are elements of the integers, we know that AD plus BC is an integer. Since B does not equal 0 and D does not equal 0, BD is an element of the integers minus the set containing 0. Thus, x plus y is indeed a rational number. End of proof, because that was our goal. So one comment to make here, you'll notice I use the word we. I know in English class, they tell you not to do that. In math proofs, that is used a lot. For some reason, mathematicians like to talk to the audience, to the jury, like they're a part of the process, right? So this is a group effort or whatever is the way we write it. So we put we in there a lot. We see that, we know that. Yeah, next we observed, stuff like that. So, all right, we're moving along. What questions do you guys have on that one? Okay, well then, we'll keep on keeping on. More proofs. Okay. So next one, prove that two integers with opposite parity always have an odd sum. So we need to figure out our if then. So we're saying if a and b are integers with opposite parity, I'm going to abbreviate opposite, then a plus b is odd. Oh, all right. We do have a question on the last one. Excellent. So why would I use the set containing 0? So that comes from what it means to be rational. I can even write that over here. So we say that some number r is an element of the rationals. That means r equals, I guess I'll use a over b, with a and b integers and b not equal to 0. So another way to say that is to say a is an integer and b is an integer take away 0. So he's any integer except 0. The set of integers removing 0. Yep. So that's, I was using that way of thinking about rational. Other questions on that one? Okay. So let's look at this one. So if a and b are integers with opposite parity, then a plus b is odd. Okay. So here is what I'm going to assume. Here is what I need to show. Let's do our scratch work. Okay, well, A and B having opposite parity means one of them's even, one of them's odd. So let's split this up. So let's say A is even, B is odd. Then we'll do A odd, B even. All right. Well, if A is even, A is 2 times some integer k. And if B is odd, B is 2L plus 1. Again, I can't use k again because B could be 13 and A could be negative 20, right? K and L might not be the same thing. So I need separate variables there, okay? My goal involves A plus B. So let's look at that. So A plus B is 2K plus 2L plus 1. So 2K plus L plus 1. And that is the form I need to be odd. I have 2 times an integer plus 1. So that is odd. That's what I want. All right. So technically on this second one, I'm starting over. I'm starting from scratch. I can use K and L again, but you could also, if that upsets you, you could use M and N. But it's perfectly fine here to use K and L again, okay? Because this first case is completely done, then I'm kind of starting from a clean slate, okay? All right. But yeah, if that bothers you, you can use M and N or something, not a big deal. All right. But notice I'm getting the exact same thing, right? Which is odd. Okay, so there are ways when we write this up, if we notice that this one looks pretty much the same, there are ways when we write this up to save ourselves effort. You know, mathematicians aren't gonna write tons and tons if they don't have to. So here we go. Proof. All right, let A and B be integers with opposite parity. Okay. So the way we can write this when you're doing cases, you can actually split it up and literally say case 1 here. Okay, so case 1, we're going to assume A is even and B is odd. Okay, then there exist K and L in the integers. We want to be sure we state their integers with A equals 2K and B equals 2L plus 1. So A plus B equals, again, you can assume they can do basic algebra. So we can even jump to this last step, 2 times K plus L plus 1. If you want to write the intermediate step, that's fine. Not a big deal, but you're allowed to jump to the last step here. All right. Note that K plus L is an integer since K and L are integers. So A plus B is odd, because that's what it means to be odd, to be 2 times an integer plus 1. All right, so that's case 1. Case 2. Assume A is odd and B is even. Okay, so now here's where we can save some effort. We're still going to do the next line the same, but then we'll save ourselves a little bit of work. Then there exist K and L in the integers with A equal 2K plus 1 and B equal 2L. So similar to case 1, A plus B equals 2, K plus L plus 1, which is odd. And we don't have to rewrite out all our logic as to why that's odd. We can just say, okay, this is similar to case 1. When I add them, I get the same thing, which is odd. So now we can write out our conclusion. And my tablet's a little annoying when I get to the bottom. So let me zoom in. Okay. So I'm going to write the word therefore. Sometimes in proofs, instead of writing the word therefore, you'll see people put 3 dots. Okay, you can use that, and that means therefore. I'm going to write the word. So therefore, A plus B is odd in either case. And that's the end of my proof. Box. All right, questions on that one? Okay, let's do, well, I think we have time to do at least one more. Yeah, we'll have time for one more. Okay. So here we have a new definition. Chapter 3 of the book goes really, really heavily into all this, but for our purposes, this is all we're going to use. So when you see this notation means n choose k, as in if I have n things and I want to choose k of them, how many different ways can I do that? So if you have 5 people and you want to choose 3, how many different ways can you do that? That's what this weird parentheses notation represents, the number of ways you could pick k things out of 5 things. Typically, we want k to be less than n, right? You wouldn't say I have 5 things, now pick 7. That's not possible. If that happens, so if k is bigger than n, we just say n choose k is 0 because it's impossible. There's no way given 5 things to choose 7 of them. Okay. So if you ever have one where k is bigger than n, it's just 0. All right. So here's the actual formula for it. Is this craziness with factorials? Let's look at a couple examples to make sure we understand it. So I had said 5 choose 3. Why don't we figure that out? 5 choose 3. So you have 5 people and you're going to choose 3 for your team. Well, according to my formula, I put n factorial on the top. So that's 5 factorial over k factorial. So in this case, that would be 3 over n minus k factorial. All right. So I have 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times, well, 5 minus 3 is 2. So I really have a 2 factorial in that second set of parentheses. So 2 times 1. So here we go. 3, 2, well, and 1s don't matter, right? Times 1, it doesn't change the value. Okay, so I canceled like terms. 5 times 4 over 2 is going to be 10. Okay, because 20 over 2 is 10. All right. Let's do another. Let's do, I don't know, 27, choose 26. Let's see what we get. So I have 27 factorial over 26 factorial times 27 minus 26 is just 1 factorial. Well, if I write out all my numbers, 27 times 26 times 25 times 24 times blah, 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 and then write out all my numbers down here in the denominator, 26 times 25 times 24 times, everything has a matching partner to cancel except that 27 in the numerator, right? From the 26, every single number is going to have a matching partner, denominator, numerator, from 26 on down. So apparently there are 27 different ways to choose 26 things out of 27 things. One final comment on this that's important. 0 factorial, when it comes up, that equals 1. And that has to do with, well, how many ways can you arrange 0 things? One way, okay? And we want that to be true because if I say 3, choose 3, so I have 3 things and I want to choose 3 things, the answer should be 1. There's only one way to pick 3 things. It's to pick all of them. So let's check it with our formula. I'll get n, which is 3 factorial, n factorial, over k factorial, which is 3 factorial, times 3 minus 3, which is 0 factorial. So you see, it's important that that 0 factorial be 1 so I can get the answer that makes sense. Okay, there's one way to choose all 3 things. It's to choose all 3 things. Any questions on that notation before we do a proof with it? Okay. Well, let's go ahead. So here's a proof. So now this one doesn't have a definite if and then. I'm just trying to show this statement is true. Okay. So that's what I'm trying to show. The hidden assumptions here is that n and k are natural numbers, well, or maybe 0. I am allowed zeros, okay? And that k is less than or equal to n. So when I use this notation, that's the hidden assumption, that I'm not dealing with weird decimals or fractions. I'm not dealing with negatives, okay? It's just 0 and positive integers, or 0 and natural numbers. And we're going to assume k is less than or equal to n. All right. So that's our hidden assumption, okay? So now we need to do our scratch work. All right. So n plus 1 over k, let's see what that is according to the formula. That'll be n plus 1 factorial over k factorial times n plus 1 minus k factorial. That's what the formula said. Top number factorial over bottom number factorial over their difference factorial. All right. Well, let's see what the other side is. And hopefully we get the same thing. So n, choose k minus 1, plus n, choose k. Well, that first one will be n factorial over k minus 1 factorial times n minus k minus 1 factorial. So that's the first one. The second one, n factorial over k factorial times n minus k factorial. All right. In order to add fractions, I need common denominator. In order to do that, I want to rewrite this first fraction a little nicer. So k minus 1 factorial. So when I distribute that minus, I get n minus k plus 1 factorial Okay, so here's what I think in my head while I'm looking at this. When I see a k factorial, that's something like my 26 factorial, right? K minus 1 then would be 25 factorial. So to get those to match, I need to multiply this one by my k, by 26. That will give me a 26 factorial, okay? So this fraction on the left, I am going to need to multiply by k over k. That will fix the k factorials, so those will match. Now let's look at the other one. Put my plus sign back in. I don't think I have enough room to fit this, but I'll try. So here I have an n minus k. Here I have one more than n minus k because it's n minus k plus 1. Okay, so that means this one is short 1. He's missing the n minus k plus 1. He has everything below that, but he doesn't have the n minus k plus 1. So multiplying by that will make that factorial match. So let's see what that becomes. So we have k times n factorial over k factorial times n minus k plus 1 factorial plus n factorial times n minus k plus 1 over k factorial times n minus k plus 1 factorial. So now I do have that common denominator I wanted. It was a little messy to get there, but I do have that common denominator. So I'm going to factor that n factorial out of the numerator. And get here. We're almost done. Any questions so far? I mean, this is a bit of algebra in here. Anybody getting lost in the algebra and need me to explain a step? Okay, so let's finish up here. Well, k plus n minus k plus 1 is just n plus 1. Okay, so this is what I've got. Now, let's look back at what our other side was. So the left side gave me this, n plus 1 factorial over k factorial, n plus 1 minus k factorial. The right side gave me this. Now I want to see, do those match? Well, yes, they actually do. I mean, n plus 1 factorial, that is an n factorial times an extra n plus 1. K factorials match. N plus 1 minus k factorial, that's the same thing as n minus k plus 1 factorial. Same thing, right? They just reordered the terms. So that means we're good to go. So let's write out our proof. In our proof, we don't need to show every single one of these algebra steps, just enough that you feel like would make your audience able to follow. So proof, let n and k, the elements of the natural numbers, union 0, because we are allowed zeros. Oh, we got a question. I don't understand how k minus 1 turned into k. Yeah, so the idea here, I had a k minus 1 factorial times a k. So if I had 26 factorial and multiplied by 27, that's the same thing as just getting a 27 factorial. So that answer your question. So I just threw in the extra term I needed to get me to k factorial, because I had every single term except that last one. Okay, cool. All right. Oh, wrong thing. So proof. Let n and k be the natural numbers union 0. Then, oh, I guess I should say with k less than or equal to n. Okay. Then, and now we put our string of equations. I want to start with the right side. So we're going to start with n choose k minus 1 plus n choose k equals. So let's write our first step, which was just using the definition. Except I'm going to go ahead and change it to the plus 1. Oh, running out of room. Plus n factorial over k factorial times n minus, here, make myself more space. K factorial times n minus k factorial. You can't fit the factorial. Yeah, come on. Well, there's a factorial there. Okay, then that equals, and then I'd jump a few steps. And you could jump to that this is maybe kn plus n times, oh, km factorial, excuse me, m factorial times n minus k plus 1 over that common denominator we found. Okay, so I jumped a few steps. Now I'm going to jump to the step that this came out to be m plus 1 times n factorial over k factorial. Let me go ahead and reorder that denominator. All right, which is m plus 1 factorial over k factorial times m plus 1 minus k factorial. And that's exactly what we wanted. M plus 1, choose k. All right, so I wrote up my algebra, and we're actually done. At this point, there's nothing else to say, right? I showed n choose k minus 1 plus n choose k came out to be the exact same thing as n plus 1 choose k. Done. We don't, there's really no conclusion. You could say, therefore, that equals that, but it seems a bit redundant. So we can declare that proof done. All right. Any questions on that one? Okay, so kind of the key point I'm wanting to get across to you guys today is just with these proofs, right? You take what you know and you just mess with it until you get a series of logical steps that goes from hypothesis to conclusion. All right. And as we go through these proofs, you're going to find, you know, make mistakes, and I'll catch them and correct them, and we'll go through, and eventually you'll get comfortable with all this. But this is just the first day. So I do recommend that you work the homework, you know, before Tuesday's class, even though, you know, you'll have more time than that. So that way you can come in on Tuesday with more questions and ready. Yeah, because this, I mean, these do take time, okay? This takes getting used to of how to go through the logic, find it out, and then write it up in complete sentences.